Hi everyone, this is Mrs. G, and today we're going to be finding complex solutions of polynomial equations. So I have a quick warm-up for you guys, so please pause the video and give these two a try, and hit play when you're ready to check your answers. Alright, go ahead and check your work here. So remember, square root method, isolate x squared, and then take the plus or minus square root of both sides. So remember, whenever we have a negative inside a square root, we're going to have an imaginary answer, so we can simplify this. Square root of negative 9 becomes 3i. And for part B, here I asked you to use the quadratic formula to solve, so plug in your values and simplify. And again, you'll see we have a square root of a negative, which means we have that imaginary number in a complex solution. So today we're going to answer the question, what if a polynomial has zeros that are irrational or complex, meaning imaginary or non-real? So today the equations we're going to be solving, some of them might be real and rational, some of them might be real and irrational, or some of them might be complex, and you might have a combination of different types as well. So to help us when we're solving, we're going to be using what's called the fundamental theorem of algebra. So it has a really fancy sounding name, but the basis of it is pretty straightforward. It says that every polynomial function of degree n is greater than or equal to 1 has at least one zero. So it's pretty much saying any polynomial equation has at least one solution. So while it's really nice to know that every polynomial function has at least one zero, it'd be nice to have something a little bit more specific. So there's this corollary that we find very, very useful. So this says a polynomial function with a degree of n has exactly n zeros. So this is going to be useful because if we know what the degree of the function is, we can tell how many answers to expect. However, we have to make sure that we are counting multiplicities, so we have to count double or triple roots as multiple solutions, and we're counting both real and imaginary zeros as solutions. So anything goes, but again, the number of solutions should match our degree. So this is going to be super useful for us today. All right, let's try this first example together. So here we're going to find all of the possible roots of this equation. So first let's look at the degree. We can see here that the degree of this equation is 3. So that tells us to expect 3 answers. Now, those might be real, they might be imaginary, they might be rational or irrational. We're going to try to find all of the possible answers. So when we have an equation, the first thing we should try to do is factor. And since there's 4 terms, we can try to solve this by using factor by grouping. So let's see if it works. So in the first 2 terms, there's a GCF of x squared. And here there's a GCF, we'll divide out -6 to get rid of the negative from the first term. So this leaves us with x squared times x plus 2 minus 6 times x plus 2 equals 0. And since these two factors are the same, we can group the coefficients into their own factor. Okay, so now that we were able to factor, we can use the zero product property. So we'll set each factor equal to 0 separately, and we can solve each of those. So on the left, we're going to start by adding 6, and then we can take the plus or minus square root of both sides. So here we get 2 answers, and then here we can subtract 2, and we get our third answer. So our 3 solutions are positive root 6, negative root 6, and negative 2. So you can see that the number of zeros that we got matches the degree, so we know that we found all of the possible zeros. So just to be clear, all 3 of these are real because we don't see any i's, we don't see that imaginary number. But the first 2, these are irrational because it makes a repeating decimal, and this is a rational solution. All right, let's try another one together. So here we have x to the fourth minus 6x squared minus 27 equals 0. So this is actually what's called a quadratic type equation, because we can actually turn it into a quadratic equation using a method called substitution, which will allow us to solve, because we know we can solve quadratics in lots of different ways. So a quadratic type solution occurs whenever your middle exponent is exactly half of your first exponent. So x to the fourth, x squared. So we can use substitution like this. We're going to say, let x squared, we're going to replace x squared with some new variable, and it's usually u. That's a really common one to use with substitution. So anywhere I see an x squared, we're going to replace it with a u. So we have that minus 6u, the 27 stays the same. And then if x squared is u, that means x to the fourth would be u squared. So with this substitution, we were able to rewrite this equation to look like a quadratic. And then this we can solve. So we can actually solve this one by factoring. Or that should be the first thing we try, because it's usually the quickest and easiest way. So what multiplies to make negative 27 and adds to make negative 6? That would be negative 9 and positive 3. So we have u minus 9 times u plus 3 equals 0. And then here we can do zero product property. So we can set each factor equal to 0. And we can finish solving. However, we're not really solving for u, we want to be solving for x. So once you've solved for u, we're going to have to resubstitute x squared wherever we see a u. So we're going to replace this u with an x squared and this u with an x squared. And that will require us to do one more step to finish solving for x. We have to take the plus or minus square root of both sides. So plus or minus square root of negative 3. And here this gives us plus or minus 3. And remember, anytime there's negative on the inside, we can put an I on the outside. So plus or minus I root 3. So looking back at our original equation, we can see that the degree of that polynomial is 4. So we should have 4 answers, which we do. So we have positive 3, negative 3, positive I root 3, and negative I root 3. So here we have 2 real solutions and 2 complex solutions. All right, let's try another one together. So here we have x cubed plus 2x minus 3 equals 0. So I know this looks like a trinomial we can factor, but this is x cubed, not x squared, so we actually can't factor it. So remember, when we can't factor, we have to use a new method to get us started. So this is where we're going to use that rational zero theorem. So remember, for this, we're going to list out the factors of our constant. So those factors would be plus or minus 1 or 3. Those are the only factors of 3. And then we list out the factors of our leading coefficient, and the only factor of 1 is 1. And then we list out all of the possible combinations of m over n. So plus or minus 1 over 1 and 3 over 1. And this is gives us a list of numbers to try to see if any of them work for this equation. So again, we have 4 things to try. We have positive 1, negative 1, positive 3, and negative 3. So from here, all we have to do is pick one, and we start testing using synthetic division. So remember, in our box, we'll put the number we'd like to test. So let's try testing positive 1. And then we'll list out our coefficients here. So we have 1. We need a 0 placeholder for x squared, 2 and negative 3. And then we're looking for a remainder of 0. So we multiply and add vertically, multiply, add, multiply, and add. So we got lucky because our first one that we tried actually works. So since we have a remainder of 0, this is one of our solutions. So one of our solutions is x equals 1. So now we're going to look at the remaining polynomial. So remember, these coefficients tell us what remains after we've divided. So this is x squared plus x plus 3. And from here, we're going to finish solving. So anytime we have a quadratic equation, we should be able to finish solving because we have lots of different methods. This one you actually can't factor it, it's not factorable, but we can solve this using the quadratic equation. So let's do that. So we'll do x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So here we get negative 1 plus or minus the square root of, this gives us 1 minus 12, so negative 11 all over 2. And since we have that negative on the inside, we can put an I on the outside. These are going to become complex solutions, so they have that imaginary number. So these are our last two answers. So we have negative 1 plus I root 11 all over 2, and negative 1 minus I root 11 all over 2. So you can see here the degree of our equation was 3, and we have 3 solutions. One of them is real, and 2 of them are complex. And you don't need to always separate this out. You could write your answer with the plus or minus sign. I'm just writing it as 2 separate solutions just so you can see that the number of solutions always matches the degree. All right, so go ahead and pause the video and give this next one a try on your own. And whenever you're ready, hit play to check your answer. All right, go ahead and check your answers. So this one we can actually factor. So you should end up with these 2 factors after you use grouping. From here, we can use the zero product property. And here, if you keep solving, we end up with plus or minus square root of negative 5, which gives us plus or minus I root 5. And then here we have 3 as our last solution. So we have 3 answers listed here, which does match the degree of our equation. All right, I have another one for you to try on your own. So again, please pause the video and give it a try. And remember, if you can't factor, try using that rational zero theorem to give you some numbers to try. All right, go ahead and check your work here. So you do need to use that rational zero theorem. Here's our list of potential zeros. So the first one that I found that works is negative 3. And we can tell again because our remainder is 0. And if you look at what we have left, it is a quadratic function, which we should always be able to solve. So this one we can solve it using the quadratic formula. Here we do get 2 complex solutions because we have the square root of negative 4, which is 2i. So we have negative 1 plus I and negative 1 minus I in addition to negative 3. All right, so the last thing we're going to talk about today are 2 theorems. One is called the irrational root theorem, and one is called the complex conjugate theorem. So the first one says all irrational roots come in pairs. So that means if you have an answer when you're solving a polynomial that is some type of radical, that's an irrational root, like a plus b root c, or even just the root c, it will always come in a pair. It would always come with a minus b root c. So you will never just have one answer that's an irrational 0. You will always have 2. They always come in pairs. And then the complex conjugate theorem is pretty similar. It says all complex roots come in pairs. So if you have a 0 that is a plus bi, then you will also always have a 0 that is a minus bi, or vice versa. So those will always come in pairs. And then you'll notice here, these both look very similar. You'll notice that the difference between this, and this is that the middle sign is changing. So this is what you call a conjugate. So that's why this is called the complex conjugate theorem. So it is really important that you know that both of these types of zeros always come in pairs. All right, so now we're going to try writing a polynomial function given its 0. So we're going to kind of go backwards from what we have been doing. So it says write the polynomial function with the least degree and leading coefficient of 1 that has these given zeros, 5 and square root of 7. So this is a rational 0. This is an irrational 0. And remember, irrational zeros always come in pairs. So since positive root 7 is one of our zeros, that means that negative root 7 is also going to be a 0. So it's implied that if this is a 0, so is this. So they're not going to always tell us that. We have to know it. Okay, so we have 3 zeros. So we're going to make a third degree polynomial. So now all we need to do is turn our zeros into factors. So remember the relationship between the 0 and the factor is that they're always opposite. So if the 0 is positive 5, the factor is x minus 5. If the 0 is positive root 7, the factor is x minus root 7. And then if the 0 is negative root 7, the factor is x plus root 7. And now to put it in standard form, we do need to multiply this out. So I'm going to start by multiplying out these two together, and we'll do FOIL. And then we'll multiply in this last binomial after. So here we get x times x, which is x squared. X times root 7 is just x root 7. Negative root 7 times x is minus x root 7. And then square root of 7 times square root of 7, since they're both square roots, we can multiply the insides. It actually gives us square root of 49 when we multiply it, and square root of 49 is 7. And then you can see here that these actually cancel out. So what we actually have left is just x squared plus 7. I'm actually going to write that first, so we can switch the order of the factors anytime we like, times x minus 5. So now we just need to multiply those last two together. So here x squared times x is x cubed. X squared times negative 5 is negative 5x squared. And then we have plus 7 times x. And then we have 7 times negative 5. And this is our polynomial. All right, let's do one more together. So here it's the same prompt, but this time we have the zeros negative 2, 3, and negative 5i. So negative 5i is a complex 0, and we know complex zeros always come in pairs. So it's implied that positive 5i, which is its conjugate, is also a 0. So again, we need to know that theorem to know that we have that fourth 0. So now let's start turning our zeros into factors. So we have x plus 2, x minus 3, x plus 5i, and x minus 5i. And then let's start multiplying this out. So I'll start by multiplying the first two binomials together, and then the third and fourth together. So if we use FOIL here, we get x squared minus 3x plus 2x minus 6. And in the second group, we get x squared, then we get minus 5 times x times I, plus 5 times x times I, then minus 25i squared. So let's simplify what we have. So in my first polynomial, we can combine like terms. So we get x squared minus x minus 6. Here in the second polynomial, you'll notice that these cancel out. So that leaves us with x squared. And then remember that I squared, by definition, is equal to negative 1. So whenever you see I squared, it always simplifies to negative 1. So this actually becomes positive 25. All right, and now we just need to multiply this last part out. So I'm going to use the box method just to help us keep our work a little bit more organized, since we have that trinomial. So we have x squared times 25, x squared, negative x, and negative 6. So this gives us x to the fourth, negative x cubed, negative 6x squared, 25x squared, negative 25x, and negative 150. And then here you can see that we can combine like terms. We can combine our x squared terms. And our final polynomial is x to the fourth minus x cubed plus 19x squared minus 25x minus 150. And now we are done. All right, here is the last example for today. So go ahead and pause the video and give it a try. And then whenever you're ready to check, hit play. All right, so go ahead and check. You'll notice here that we were given -1 and positive 2i, but since this is a complex zero, we know it will always come with its conjugate pair, so -2i is also a zero. So turn your zeros into factors, and I started by multiplying my two factors with the imaginary terms to get this. So remember, whenever you have I squared, it simplifies to -1. So this actually becomes positive 4. So we have x squared plus 4. I put that factor first, times x plus 1. And if you multiply that out, you end up with x cubed plus x squared plus 4x plus 4. Alrighty, that is all for today's video. Thank you so much for watching.